science like there's no tomorrow.
Welcome everyone to the Financial Engineering course. Today is the lecture number 2. The main subjects of today's lectures are filtrations, expectations, conditional expectations, and measure changes. Those three important elements, so the filtrations, expectations, and measure changes, are really crucial elements that we are going to use later in this course for derivative pricing. Especially in the world of interest rates, it is very important to have to be very fluent in using all those three tools. Let's take a look at the content of today's lecture. Today's lecture is divided into 3 blocks. Each of these blocks is about 45 minutes, and it will be released within a few days. So there will be a few days in between. I think 45 minutes between a block, it is just enough. I know that if the lecture takes more than 2 hours, 1.5 hours, it's not maybe the most exciting one. So today I decided that the course will be divided in 45 minutes slots. So the first block I will discuss filtration, conditional expectations, and conditional expectations in Python. So those 3 elements, like here actually change of measure will be discussed later, but filtration and conditional expectations. I will show you how it is important that you understand the filtration, how this filtration can be some kind of related to traveling essentially in time, where you have to decide what is known, what is not known, and what is actually this is related to the concept of measurability, what is known in the future, and how this relates to derivative pricing. Then I will show you benefits of conditional expectations, so how powerful this machinery of conditioning on random variables that are stochastic. Of course, random variables are stochastic, but how, if you have multiple, let's say, dimensions, how to use this concept of conditional expectations to really enhance your simulation, how to include information about your model, for example. So imagine this scenario where you have complicated model, and you know that your model, after simplification, will becomes let's say simple Black-Scholes, so something that you can really handle easily. With a conditional expectation, you can incorporate this knowledge into the simulation and also into pricing. And that's also I will show you in this in the first block. So I will discuss conditional expectations, and also here we will cover the concept of a nested Monte Carlo. So this is how to think of conditional expectations, filtrations, and how to perform simulation in Python. This is the first block. In the second block, we will go into a pricing of derivative using conditional expectations. So here I will focus on showing you a process. In this case, we were using Black-Scholes model with jumps, stochastic jumps, and the application of conditional expectations to enhance the convergence of Monte Carlo simulation. So you will see that by incorporation of conditioning, the convergence is significantly improved. So this means that you may need fewer paths that if you just apply brute force approach and just simulate the model and price the model using all the Monte Carlo paths. Then we move to the concept of numerier, and what is it? Yeah? What is the measure change? What is the Grzelak theorem? And I will mainly concentrate on really tips and tricks. I will show you how to use the measure change without going into much details on the theorem itself. I will show you how to, from the engineering perspective, how to use the concept of measure changes to really benefit, and how to change measure between different numeriers. So if you have numerier, how to use it to measure transformation. And also in this block, in the second block, I will show you how to change measure P and Q. So P measure is typically associated with a real world measure. So for example, you have a model for which parameters are estimated from historical data. That's typically the P measure. And measure Q, it is typically linked to derivative pricing. So it is implied measure from the market instruments available in the market. And then of course we would like to switch from one to another one, and I will use the concept of numerier and measure changes to achieve that goal. And the third block, it's a really nice one, because here we will be applying what we have learned in the previously about measures, filtrations, and expectations. I will show you how to think of a measure which is a stock, so numerier as a stock, and how we can benefit in pricing. Then we will go into dimension reduction, so how measure change can be used to reduce the dimensionality of the pricing problem. Then we have a forward measure, so something related to stochastic discounting that we will be encountering we will encountering many times in this course. So this is, I would say, the key measure that we have to learn, and I will apply many times in this whole course. This measure is typically associated with stochastic discounting, where you have a derivative, let's say a stock. However, the discounting takes place in stochastic way. So in Black-Scholes case, for example, the discounting was deterministic, was constant. In a generic case, that would not be the case. So then you have a stochasticity in how to remove that element, the stochastic element, by using the measure transformations. And finally, we have a summary of this lecture, and I will also give you a few exercises. I think there will be 4 or 5 exercises, homework exercises, that will involve simulation. So there will be a task of programming something in Python, and also derivations, some martingales, stochastic differential equations, etc. I think using this homework, and also by following the lecture, I think you'll be well skilled and you have enough knowledge to continue with the course, and I think you will enjoy it. So welcome to the second lecture. Like I mentioned, we have 3 blocks today. In general, we have 3 blocks of this lecture. Each of these blocks is about 45 minutes, and it will be released each block by each other, I think after each other, after a few days. So enjoy, good luck, and enjoy also the homework. Don't forget about that. When dealing with stochastic differential equations, you will always encounter the concept of filtration. It is very important to understand what are the main principles and how to use filtration in a proper way, especially in the interest rate world. The concept of filtration, and also when we deal with XVA or simulations, filtration, it is integral part. It tells us where we are, where is the time, how to look at the time. Especially if you think of simulating some kind of exposure profiles, risk profiles, you always need to understand, you have to put yourself in a perspective of, let's say, traveling in time. You are in a particular path, particular realization, and then you're looking from that perspective at your, for example, the portfolio values. Let's look for the mathematical sense how the filtration is defined. First of all, we of course start with a stochastic differential equation, or stochastic process, which is a random variable. So if we have xt without time, it will be just a random variable, like a normal random variable or exponential, whatever. If you add additional index, then we talk about the stochastic processes. So every time we have a time element, we have a variable becomes a stochastic process. And then because we have a time index, then a stochastic process is simply a collection of random variables indexed by time t. What other thing is very important is that typically we have some simulated dates. Yeah? So you can think of some kind of exposure dates or dates at which you would like to see the value of your portfolio. Those are your T1s to up to Tm. We always have today's date. This is always very important. It's always kind of a reference where we are today. So today we can observe certain market data, and that market data can be used to simulate future realizations. And that will be very clear in a few slides. And then, of course, up to today. So we know the history up to today. Everything which is happening after today is the future. And then the concept of filtration is very important to understand what it is. The past is known. So in the filtration, we always indicate what is the history, where we are, and what we know. So that's kind of you can see it as a limit. Yeah? So the filtration tells you at which point in time, what knowledge you have about your history. So it could be, for example, that your filtration is in the future. This means that you have to imagine that you are in the future, and then you have to ask yourself, if you are at that point in time, what quantities you can observe at that point in time. It doesn't mean that those things are deterministic. They would be deterministic, of course, if you are there, but they are stochastic from today's perspective. So always this concept is it's very important to distinguish when the filtration is up to today or filtration is in the future. In a computational finance course, we mainly consider the case where filtration was ft0. So we always had the filtration, maybe you remember, was always t0. This means we had the knowledge up to today. So today was t0, and then we could use, for example, initial stock value as t0 for pricing, interest rates at t0, and so on. However, in today, and also in the lectures ahead, this filtration, it won't be only t0, it could be future times. And today will be very clear for you what are the advantages of using of this filtration, different filtrations, how we can even, by simulating, how we can extract computational efficiency. This is very important. So for the future, of course, we don't know the paths. So we know the path. So we can say the stock realizations up to today. So if we have a time frame, we have a stock which is the history of the stock, and of course everything which happens after today, it is stochastic. We don't know it. We try to describe the stochasticity using some stochastic differential equations, some simulations, and the past is essentially only one path. So you can think of you try to choose a model which will generate, let's say, Monte Carlo paths for the future, all the possible different type of simulated paths for the future, and market or reality is choosing only one of them. So that's a kind of also a very important concept. But of course, like I say, the future we can always simulate, and hopefully if you have market instruments like call options, we could know even the distribution of the future date. So if you have some certain time, capital T, then this distribution, it can be implied from today's information. Of course, it doesn't mean that this will happen. It only tells you, so if we have call options and we apply distribution at a given time, that means that the distribution represents market expectations about outcomes in the future. So this is something important to understand. But of course, later in this course, you will see more examples, and we'll go much detail into details. We'll go much more in depth in the concept of filtrations and usage. So this is what I just discussed. So we are today, it's here T0. We have past. So past you can consider as the only one realization, one single path that reality is picking from all the paths we have simulated. But since we are today, we know exactly what the history was. And then we have a concept, of course, that we simulate the future. So our role is to generate scenarios implied often from the market instruments that could represent all possible cases, or not all, but many possible cases, that realistic cases that could happen in the future. And of course, we don't know which of these paths is the most realistic one. We just know that there is uncertainty. So we have a distribution here at this point, for example, of the outcomes. We have distribution here. We also have distribution here. And of course, closer to today, this distribution becomes narrower and narrower. So if, for example, we are in this area, this distribution is very narrow. This means that uncertainty related to tomorrow's market situation. So for example, if you look at the stock, where the stock could be tomorrow, of course, it is much more limited. If, for example, we think of stock, how it could behave in a year or two. So maybe you remember from the course of computational finance, always we have this concept that the growth here, it will be on average sigma square root of time. Yeah? So this is the volatility effect, and time effect is always a square root of time. So here you see that we go in time, and then uncertainty is increasing in time. You see it increases in a square root of time. And that's basically more further in time, more uncertainty, less wind, essentially. And of course, often these distributions that we have here, we have two options how to estimate them. We can estimate using historical data that's typically associated with measure P. So if we have a process, stochastic process, and we calibrate the process to using historical data, using, for example, regression or some calibration, that's typically associated with measure P. On the other hand, if we use market instruments, for example, options or some stocks, or no, maybe not stocks, maybe stocks, historical stock realization will be actually P. If you use market instruments which are on the market, for example, options or other derivatives, then we typically talk about calibration of your paths using Q. This measure Q, is often associated or mainly associated with pricing, and also to some extent you can think of risk management. So what is the market perception of the risks associated with realizations? And measure P is typically risk management. So this means using, for example, a model, we can historically calibrate the parameters and see how our portfolio would change depending on the history. Of course, the question, you cannot really, if you think of a risk management, it's difficult to decide which of these measures is the most appropriate because they're not unique. You cannot really say what will be the future. We don't know what is the future of a certain derivative. However, we can try to estimate or generate scenarios like we see here using either market perception, what market is expecting, or some historical data. Some people, for example, also consider stress scenarios. So, for example, looking at the market behavior in the stress period, for example, within market crash, well, let's say 2008, 2009, and that period could also be used to generate future scenarios. And based on that, you can have a conservative measure of your risk profiles. So now if we look at the filtration, so filtration, it is essentially, mathematically, it is a sigma field of certain random variables. Here you can see that filtration is knowledge that we have at given time. So if we have times t0, so this is today, t1 and t2 and so on, of course, the later in time we are, this has the biggest knowledge. Yeah? So if we would be here at this point, of course, imagine you are at that point, you know everything, you know exactly that there was one path that went there, so came to that moment. Of course, we don't know it yet. So bigger the filtration, further filtration in time, it tells you how much knowledge you have. So of course, it means that the filtration today will be always smaller if we would travel in time to tomorrow. And that would be definitely a smaller filtration if you would travel in time a year ahead. Because at that point, if we would be a year ahead away from today, so it will be 1 year, let's say 2022, 2025, and so on, at that moment, we would have much more information that we have today. So this means that filtration has all this historical knowledge. It's bigger than the previous historical dates. So more in time, further in time we go, more knowledge, more information about the market we have, and it's certain because that already is realized. So the concept of measurability also is very important because if we have a stochastic quantity, we need to know at which moment we know them or they are uncertain. So for example, if I look at the stock value for a year from now, but I'm looking from today's perspective, that's not measurable, right? So if I look at the expectation, for example, of stock ST with filtration FT0, this means it is not measurable. I cannot just say this is ST, right? Because filtration, which I have here, is only up to this moment. However, I'm asking for stock for the future. So it is not, I cannot say it is just measurable, I can take it outside the expectation. However, if I would have here ST0, then of course this will be the case. So then I will have here ST0. Because today I know what is the stock value, so then indeed it is measurable with respect to that filtration. So always when you have an expectation and you think of measurability, you always have to look what time is indicated by the filtration and where is your variable. So if your process that you have is before or after that time t0. So of course here st0 is known at time t0, so this means it is measurable. If st would be in the future, it is not known at time t0, it is known in the future. So for example, if I take expectation of S, so this would be expectation of ST filtration here, we have a T, capital T, then it is measurable, of course. So of course, so this is nice to see. Yeah? So we have expectation of S capital T, filtration capital T. Of course, it is at that moment in time, at time T, ST is measurable with respect to that filtration, so it's ST. So typical mistake that people make is that they assume, okay, so this is measurable, so it's a number. But of course, it's not a number. It is a random variable. So this is, you see that here it is essentially it's the essence of the filtration issue that I often encounter, that people think, students often think that if something is measurable, this means it's constant. No, it's not. This expectation here, it is expectation of a stock given at given time, so expectation of a stock in the future, given that I know what is in the future, then indeed that would be the future realization. But from today's perspective, this is unknown. So this filtration here, this is filtration as we would be, let's say, a year or 2 years or 5 years later than we are today. So then from that perspective, this is indeed measurable, so it's known. But from today's perspective, this is still stochastic quantity. So although it's measurable, it is still stochastic. So let's have a look here. So this is exactly what I just mentioned. So we have xt1, which is ft1 measurable. So you see this is the same case here. So the expectation, it will be just basically a constant with respect to that filtration. But from today's perspective, it is still stochastic. So, however, indeed, so xt1 or st1, it is a future realization, so which is not known at today's. So this is the illustration. We have a historical path. We simulate something into the future. So a stock, it indeed will be measurable with respect to ft1, but we are still here. So it is still stochastic quantity. And like I mentioned before, further we go in time, so further we go here, those filtrations become bigger and bigger and bigger because, of course, they know all the history. So, of course, older you are, more you know, hopefully. But and also the same works for filtration. So filtration tells you how much knowledge you have at a given time. This is something related to this traveling in time when you think about the process and stochastic processes, where exactly you are, how you calculate expectations. So here I would like to bring you some a comment from mine. So it's a filtration and measure changes. So basically those two things always go together. They're really powerful tools. And if you know how to use it, it can be extremely powerful. You can really benefit computationally, and also often you may not realize, but using filtrations and measure changes properly, you can really often find a solution analytically. However, if you look at the first glance at this problem that we have, and actually this will be discussed also in this lecture, this problem seems to be very, very difficult, but with help of measure change, you can really find things analytically. However, if you make a small mistake, then the costs are really big. So if you do it inappropriately, so then the things may go completely wrong way. And this is related to the Back to the Future movie, of course. If you know how to use your tools, if you know how to travel in time, if you know how to use your filtrations, you can really benefit from it. You can really learn and you can really exploit the tools and the models you have in your portfolio. However, if you make a mistake, then it takes quite some time to really fix it. And then indeed, often you have to go back to square one and really untangle the problems you have made by simple mistake related to filtration. Here's a little bit of mathematical description. So if we say that the process is ft measurable, we mean that at any point in time before capital time t, we know the realization of this process. So like I said, if we are today, we know exactly the history of a process, and then it's known. So it's deterministic and it's known. And this, of course, it's an example where we have a stock value and we look at the historical values. The stock today is always measurable. So this is also what we have just discussed. If you talk about expectations, expectation tells you the average essentially of the realizations. But if you have a stock today and you take average of a value that you see in the market, of course, it is the same value. So it is stocks today is also measurable. However, if you think about the future simulations, they need to have a model, and then it's often related to distribution of a model. And then this means that you have to calibrate somehow your model that you will use for simulation of the paths, and that will be often implied either from historical data. So for example, you will calibrate your parameters of your SDEs, stochastic differential equations, to historical market data, or you would imply it from the from market instruments. And then we have another thing is that sigma fields or filtrations. So if you have a variable sigma field xt, it is included, the knowledge about a process xt, it is included in filtration ft. And the very important concept that you may already have heard, it is when we talk about the processes which are adapted. A process is adapted, and basically it means it does not look into the future. So if a process defined xt, it's only the knowledge, only relies on the information that is known until that moment, then we can say that process is adapted to certain filtration. And some few examples. So the first two examples are of adapted processes. So Wt is a Brownian motion, and we have a Brownian motion here at time t. Then we have a Brownian motion squared minus t, and those are two, for example, they're adapted. Of course, Brownian motion at time t, it does not look into the future. It only relies on the history of the process. If you simulate, it is independent increments that you put together, and then you know that everything at that moment, you don't know information, you don't rely on the future realizations. Those will be random generated from your model. And the same here, of course, this element squared does not really change anything. So if we have a random variable and we have squared, the dependence, whether it's something measurable or not, does not depend. So you can have here power 1,000,000. It does not change the quantity of let's say measurability of a process. So you can choose whatever function you want, as long as it's continuous and there is no let's say regular function that you would consider in finance, then this will be always measurable. And this element here, minus t, of course, this is just a constant. It's a deterministic function, so it does not look into the future either. It's just a number. And of course, here we have another example where we have two variables. So we have maximum 0 st. Of course, this means that we look at the path of Brownian motion. So Brownian motion starts at 0. We look at the path, and we are here until time. Here is t, small t, and we look at the maximum value of this process. And of course, or squared, yeah, so squared will be much more exposed. Of course, this is, whether it is a maximum, minimum, or it's a square, you see that this doesn't look into the future, for example, here. It is just historical information about the path realizations. So obviously it is measurable, it is just historical realization. So of course, this is adapted. Those two processes are adapted. And square, or whatever power you will have there, does not really change the properties of process to be adapted or not. The examples of that the process is not adapted, it is, for example, here. So always when you talk about adaptation, we always talk about with respect to which filtration. So we have an ft here and here. So also ft, so wt plus 1, it is not adapted to this filtration. As you can see, at time t, process relies on realization in t plus 1. So this means it looks actually in the future. So if you're at time t, the process relies what will be at that moment. So this means it's not adapted. And the same here, although this part is adapted, capital T, which is after small t, it is also makes it that the process would rely on some realizations on the capital time t. So this means these combinations are not adapted. In every introductory course, like for example, financial mathematics, you learn a lot about expectations, about linearity of expectations, power property, and so on. Now we focus on power property, which is extremely powerful tool once we talk about pricing. Power property is essentially relation of sigma fields, so filtrations as we have just defined, and also expectations. I'm pretty sure everyone remembers. Of course, after given some conditions, so technical conditions, the second moment is finite. X belongs to the L2, and then L2 is indicated by the Hilbert space. We define properly a probability measure. I'm pretty sure that you have seen this equation when you have expectation of X given some filtration. So you see this filtration G, it's the one which is contained in filtration F. So we can here see that this could be, for example, FT1, and this will be FT2, because filtration FT2 is much bigger than ft1, or it's bigger than ft1. Then we know the relation, that there is an expectation, and then we have inner expectation, so the outer expectations is with respect to this filtration. So it is exactly as we have had here. However, we have extra term, or not extra, but instead of x, we have a conditional expectation of x given sigma field, which is much bigger one. So although I'm pretty sure that there are not so many exercises, or you may not be able to really indicate how to use this property, it is extremely powerful tool in financial engineering. Imagine a scenario where, for example, you have an expectation of some function x, and we have some random variable y. What is important is, for example, that if you look at it, this function f, if it will be only function of x and y will be deterministic, let's assume that you know it analytically, this expectation for this function. So, but because we have 2 dimensions, this is not so easy anymore, and it's not trivial because maybe you don't know the joint distribution of function f. But what we can do is, because of this property here, we can condition our expectation. So we take expectation, and we have also second expectation of our f x y given y, and then we condition on y. So basically what it means is that this is y here, erase it here, eraser, we have here, so this is a y, small y. Because we have used the property of a Taylor property of expectation, essentially this means that this inner expectation, we can solve it because we know that for in this expression, we have y, which is only a function of, it's deterministic for a given y. So we see, because we condition on a whole random variable, so we look at the particular realization of y, then this conditional expectation is basically a function only of x. Y is deterministic. So we started with an assumption that our expectation for function x, if we have only one variable, we know it. If it's 2 variables, it's much more difficult. But because of the conditional expectation, we actually have an expectation, the outer expectation, and the inner expectation is something that we feel familiar with, because this is exactly what we know how to calculate. And of course, we need to essentially, if y would be stochastic, what it means is that we have to simulate multiple y's. So how many paths we can consider for our process y. For each of those realizations, we have to evaluate this inner expectation, and then at the end, we take expectation, the outer expectation. So you see, it is extremely powerful. In a few slides, we will look into the Python code where we use exactly the same principle. We will use the Taylor property of expectation. We will apply this property to pricing of a derivative. We will price a call option based on Black-Scholes model, where the volatility is not constant, it's not time dependent, but stochastic. In that way, we will improve the convergence of the method, and also essentially we will benefit a lot because some part of the problem is known analytically, and that's always very advantageous if we talk about simulation. So whenever we have a simulation and we can extract parts that we know analytically, you will always benefit in a simulation sense, because then Monte Carlo doesn't need to converge in particular aspect for which we know the solution analytically. If you go further, if we have the same condition, so this is just maybe this is more appropriate here. We have to our particular concept, because we are not dealing with filtration. We have random variables with filtration. So we see the same as here, except now we have sigma fields generated by random variables. But essentially, you can consider this as time filtrations. But in this sense, this means that the random variable also doesn't have this knowledge or about why it is included in information of x. If we talk about the stochastic differential equations, this is always related to particular filtration. Once we know this is also maybe also related why I said we could actually calculate this expectation. It is actually related to the definition of the conditional expectations. So if we have 2 random variables, continuous random variables, then by definition of a Taylor property, we have an outer expectation here, we have an inner expectation here. By definition, we look at that we have integral inner expectation of y given x is equal to x, we multiply with probability of x dx. So you see, this is essentially the expectation for which we know the expression analytically. This, like I just said, in a simulation, if we can condition on a random variable, then, and we know the answer analytically, then we only have to, let's say, calculate this outer expectation where we perform the sampling, say, of this x. We just, for every sample of x, we would just calculate the inner expectation and take the average. Of course, integral times the density, here it is equivalent if by taking average for multiple or many realizations of x, and then just we calculate average of this inner expectations. And then we can also express in this term, but of course, if we talk about simulations, typically we don't know, especially in finance, those conditional densities or two-dimensional densities that are hardly ever known analytically. Much more often you're encountering a case where you have, let's say, multiple stochastic differential equations, and by conditioning on some of the parameters or some of them, you can actually find analytically conditional expectations. And this would be example we will see in a few slides when we talk about the Black-Scholes model and condition. Although we have a process with jumps, stochastic process with jumps, it's two-dimensional, I will show you how to reduce the dimensionality essentially of an outer expectation of an, let's say, average, of inner expectation, which is simply Black-Scholes for realization of the variance. And that will be shown in a few moments. And this is another property that if we have this filtration, so if the proper relations between the filtrations of x and y holds, if we take outer expectation of y given x, essentially what we will arrive is the expectation of y. So we always have to make sure that your filtration in the inner expectation is always bigger than outer expectation. Then you have this property. So the conditioning on something which is of wider scope, then you have this beautiful relation. And of course, let's go back now to the two elements that we have discussed so far. So the conditional expectations and filtration. So if we consider today t0, we have some future time t1. So it's again, we are here, t0, we have time t1. We have a process, so it simulates process. And we are looking at the expectation of the process x at time t1, which is conditioned on this filtration here. Of course, because we know its process xt1 is measurable with respect to filtration ft1, then we simply get xt1. So that's our answer. And of course, that's correct answer. And the question is this null? And the answer is not. It is still stochastic quantity from today's perspective. Because you see, here the conditional expectation was as we would have traveled in time until time t1. Of course, if we are at time t1, xt1 is known. However, from today's perspective, it is still stochastic quantity because we don't know it today. We will know it only at time t1. So this is, keep that in mind. This is very, very important. Something that we don't know about that you see, for example, index in the future. This is something to be alerted that this is typically stochastic. It's hardly ever to happen that it will be deterministic. And this is, I think, the most important takeaway once we talk about filtrations and conditional expectations. This is the very important one. This is first reason, for example, if you have a mistake somewhere in your code, always make sure that you have properly used conditional expectations and let's say filtrations. And the second most important takeaway is how to use those conditional expectations. So if you know something, if you have a complicated model which depends on, let's say, two or more stochastic variables, and you can calculate this outer expectation and inner expectation, you know, then you can always benefit from that, because if you can impose, let's say, analytical solution even to the some part of your model in a simulation sense, you will always benefit from that. And we will see in a few seconds what are the benefits in terms of convergence. Before we dive into conditional expectations and pricing of derivative, let's take a look at something simpler, but also very, very important. In this Python experiment, what we're going to perform, we have two tasks. Point A is about calculating of a expectation, conditional expectation of a Brownian motion. So we have a Brownian motion WT. So it means we simulate Brownian motion from time t0 until some time t. And we take expectation conditioned on time t0. So of course, that's a very simple experiment because we know that initial value for Brownian motion at time t0, it is 0. So essentially, the first point is equivalent with taking expectation of all the paths at this point. So we take expectation of all those paths at time t. However, look at the second point. Second point is much more interesting and also much more difficult because now we have an expectation of WT given S, but S is also in the future. So this is not T0 anymore. We have a case where we have let's say a future perspective. So this is not good. So we have some point S, we have time point T, we have a Brownian motion, which is simulated up to this point. And we are asking, okay, what is the expectation of W time T? So this means that from this point, so we have paths. Essentially what you can see actually from here, if we are at this point, we have multiple paths going all the way here, right? Because we assume we are at this point. So this means we are serving some simulations for every path until this time point, and we take expectations of this conditional paths given the filtration of at time fs. So you see that this is kind of tricky because the answer, of course, if you just take expectation of all those paths of Brownian motion at time t, the answer will be just constant. But here we expect the answer to be, because this is measurable for filtration fs, so this means that we would expect the answer has to be stochastic. So you see, for every path, essentially we are obliged to do the conditional sampling, and then for each of those paths, we have to take expectation, and then we do the second simulation of a second path, and you see that there's a second path. Also, we have to do sub-simulations, and then we take a second expectation, essentially. And then we do the third path, and then we do all the simulations for those paths, and then we have a third conditional expectation. And once we collect all of the conditional expectations, then we will end up with a Brownian motion at time s. Maybe you can ask why this property holds. I hope that you already had you know this. So this is related to the fact that Brownian motion, we can actually say, we can always write Brownian motion at time t as Brownian motion time t minus ws here first, and we add and subtract, right? So this is, you see, this is equivalent because this will just cancel this. And then if you look at the expectation, conditional expectation, WT, it is fs here. We have expectation, conditional expectation of WT minus ws. I will do it because we are using the linearity of expectation. Then we have here S, and here we have a plus expectation of WS even filtration to S. So of course, this part, as you may remember, we have a property of independent increments of Brownian motion. So you see, as long this interval, so we have a time S and T, and we have a second, so filtration until point S. So the first interval is from 0 to S. This is for filtration, is this part, and T minus S is this part. So here we have this interval. As long they are independent, so they are not intersecting, we use the property of independent increments. This means that this expectation is just 0. And here we have a Brownian motion time S conditioned on the filtration at time s. So this is simply equal to ws. But this is, I may be repeating this, but I'm pretty sure you already knew the answer before I have asked the question. So here you see that basically, if we would like to simulate this kind of thing, we would like to condition on a future time, so it's not conditioned on time t0. This requires some much more computations there, because this means for every path we have to perform sub-simulations. Often this is called nested Monte Carlo. This concept also is present in computational finance, and essentially whenever you need a problem where you have conditions on some time, you simulate it and you ask what would happen if I would be there and I would like to see the option value, then we have to think of nested Monte Carlo. Let's take a look at the Python code. So I prepared some codes where we could simulate. We can see the impact of the calculating of the conditional expectations. So I have chosen two types, time S and time T. We have 1,000 paths and 10 Monte Carlo steps. The first martingale, so this is the one that is an easy one, because we just simulate Brownian motion, and then we take expectation. Because at time t0, we know all the paths will always start at time t0. So Brownian motion always starts at 0 at time 0. If we think of a future time, that would not be the case anymore. And then for the martingale B, where we look at expectation of WT condition on filtration at time ts, then we need to have a nested Monte Carlo. First, what we do, we simulate Brownian motion until time s. So this is the first point we are interested in. So we simulate, this is from 0 to s. So it's a standard procedure. I also do some standardization here. So for people, I hope you have seen it already in a course of computational finance. If not, I would recommend to take a look there. So this standardization ensures that Brownian motion, it's constructed from independent increments, which are standard 0, 1, actually scaled with the time. And by scaling it, so making sure that at every time step we have a unbiased random normal, we just scale it by subtracting mean and divide it by standard deviation. And that helps with the achieving convergence, better convergence, because we know exactly what the properties we expect from random samples, so we can enforce these properties on Monte Carlo simulation. But more details on this, please, I refer you to the course of computational finance, especially the chapter of a lecture on Monte Carlo simulation. So first we simulate Brownian motion until time s, and then we we look at the last column essentially, because that's the most important, because we simulate until time s, we are looking at the conditioning on the filtration time s. So we know that there will be multiple paths. Actually, it's 1,000 of realization, because we have here 1,000 paths. Then for each of those paths, we have to perform nested Monte Carlo. So for each path, we basically redo the experiment of simulating Brownian motion with different initial, which is given at time s, and then we take expectation. So this is this part here. So we take number of paths. We assign here for vector WT initial value from the paths from WS. So this is the WS, because WS now, you see, it's just a vector taken as the last column from Brownian motion simulated until time s. And then we simulate Brownian motion given that initial point. You see, that's basically we have WT. And then this is the iteration where we build up Brownian motion given the initial determined at time s. And then what I'm doing next, I'm calculating the expectation. So for each of those paths of nested Monte Carlo, I'm taking the expectation, and I'm calculating also the error, because the error, we know we should measure it as the expectation, conditional expectation that we are on particular path, minus WS, which is actually the path which we generated until that moment. And here there's some plotting taking place. So for the first path, I would like to illustrate the simulation of path until time s, and then nested Monte Carlo. So let us run this. It should be rather fast. So these vectors here, those outputs, this is for each path that we have. We compare the conditional expectation conditional expectation minus the path of WS at time s. So you see that everything nicely, its error is very small. And this is the illustration of for one path, the nested simulation that we have to perform. So we have a simulation of Brownian motion of one path until time s, and given that path, we have to perform sub-simulation and then take expectation of this quantities here, and this expectation is the conditional expectation of a particular realization at time s. And then we have to repeat and repeat and repeat for as many paths we had at time point s. So you see that although simulation of Brownian motion, it is rather straightforward and cheap. If we think of conditional expectations, then we have to have a nested Monte Carlo, which involves, in this case, will be 1,000 times we have to perform simulation of Brownian motions, because for each path we have to do the nested simulation.